I have deleted most of our code. Actually, I didn't delete any of it. I put it over here for safe reference because in this video I just want to simply introduce you to the stack, and then we'll come back to our original example and kill the redundancy that we saw. First of all, notice I left our static data, and the reason why I call it static is it will exist and always be there for the duration of the program. Thus static. Always there. It's not dynamic. It doesn't come and go and change and that kind of thing. It is there. All right, and we've seen examples where I can say inc count and I don't know, add power value 8, and let's increment count again, and increment count again, and I can all day long, I don't know, 99 inc. I can even inc power. It doesn't really matter. All day long, I can randomly access these variable names, count and power and count and count and power and so on and so forth. It doesn't really matter what order or how I access this memory. In fact, that's one reason why memory is called RAM, random access memory. It doesn't matter. Let's go out here and write this location and write that location, read that location. Doesn't matter. Okay, the stack is just another section of RAM. No different than any other RAM, no different than the static memory, even dynamic memory, heap memory as we call it, that I'll show in future videos. It's no different than either one of those pieces. It's still bits and bytes. All right, that's it. However, the way that we access that memory is different than how we do it here. And this is simply by definition of the architecture of what we're going to use. We could certainly use some indirect ways to do some scary stuff. I'm not going to get into that. Let's talk about the stack. First of all, the typical computer science example is a stack of dinner plates at a lunchroom. All right, I would almost do you harm if I didn't use this example, because every single computer science course I know and book that I know is when we're talking about the stack uses the example of dinner plates in a lunchroom or a cafeteria. You and I go to the cafeteria, and here's a stack of plates, and I want my food, so I take the first plate off the top. Then you want some food, so you take the next plate, and Billy behind us takes the next plate, and so on and so forth. We take these plates off one by one, and this is called popping off the stack. All right, but as we get lower here, the lunchroom workers realize, we're running out. Let's push some new plates onto the top of the stack. We don't want to run out of plates. In fact, one time I was at a buffet and that happened, and boy, chaos ensued. Anyway, so they just pushed all these values off, and then more people are going to come eat, and they're going to pop values off. Well, the stack in memory we use the exact same way. Let me show you. I'm going to come here and I'm going to say push, 8, and let's push 14, and let's push whatever is sitting in EAX. I have no idea what will be in EAX at the time, but let's push it anyway, and I can even push EAX again. All right, and I don't know, let's push one more value. Let's do 72. All right, well, in programming memory, we have a stack as well, and we're going to push an 8, so here we go. Here's the value 8, and an immediate value here will be 4 bytes wide. That's kind of important to keep track of. Push 14. Well, here we go. We're going to push the value 14 onto our stack. And then let's push EAX, which I don't know what will be in there at the time when we execute our program. It's going to be some rubbish. I'll just throw EAX out here for now. And then right here, let's push EAX again. All right, again, the same rubbish, but identical rubbish to the rubbish we've pushed before. Then up here we're going to push 72. All right, this is called a LIFO data structure. All right, when you hear stack, you should think LIFO data structure. Last in, first out. Okay, going back to the plates over here. Notice this plate down here at the bottom, if the workers keep pushing plates on faster than people can pull them off, this lonely plate will lead a sad life and never ever be used to be eaten upon. And last time I checked, dinnerware loves to be used. At least that's what I learned in Disney's Beauty and the Beast. Anyway, the last guy in is the first guy out. Well, the last guy or last plate to come onto our stack will be this one. We're pushing one in. That's the last one in. But notice it will also be the first one out. All right, the worker just pushed this plate on, but I'm hungry. I'm going to make that the first plate out. Okay, that's why we call it LIFO, last in, first out. Now you don't need to memorize that if you don't want to, but it would certainly help your computer science knowledge. Let me go down here, and I'm going to say pop. And when I say pop, that's going to take the last value that I pushed into the stack, is going to pop it off, but I have to pop it to somewhere. I just can't say pop, unfortunately. I wish we could. Anyway, let's pop it into EBX. All right, and let's pop into ECX. And we can pop into ECX again. Doesn't really matter, but for consistency, I'll put a DX there. And then for inconsistency, I'll pop EAX there. And I can pop all I want to. All right, what's going to happen here? Well, EBX, let me draw our registers here, like so. This will be EAX, EBX, ECX, EDX. And again, this is memory on the CPU we can randomly access, but it works differently than the stack. When I say pop EBX, that takes the current value at the top of the stack and copies it into here. So I said BX, so 72 right there, but it also takes it off the top of the stack. All right, 72 was the last guy into our stack, but now it's the first guy out, and I just popped it into EBX. Okay, let's do the next pop. Pop ECX. Well, whatever rubbish was in EAX that I pushed onto the stack here, I will pop it into here. So now ECX and EAX will look very similar. I'll just write EAX here for the rubbish that we get. But again, pop takes the value off the top of the stack. All right. Oh, look at this again. We pop EDX. All right. So EDX is going to take this value off the top of the stack, which is, again, EAX rubbish. So EAX will be the exact same rubbish as ECX, which came from EAX. EAX is just, it's kind of like cancer, polluting the registers with the value of EAX, but whatever. Whatever. And then look, let's clean out EAX. Let's pop into EAX. That will put a 14 right here. So it copies the 14 out, and then there we go, it's gone. Like so. And then, hey, we have an 8 here. We didn't pop it off. We didn't pop it off. What's going to happen? You know what? I'll tell you, bad things are going to happen, but I don't want to talk about it in this video. So let's just pop into ECX. Let's clean ECX out. So that will take this 8 and copy it. We'll copy it into ECX. Right here, that's an 8. There's our lines again. And it'll also remove it from the top of the stack. So we're going to see the stack a lot. We're going to examine it, use it a lot, and I'll show you, probably not in the next video, but very quickly, I'll show you, hey, if we didn't do that extra pop, what kind of bad things can happen? Bad things definitely can happen. But in the next video, I want to actually walk through this code and show you how it works and view it in the debugger